This next section, 6.1, is certainly one of the most important topics we have in our entire physics course. This concerns work or equivalently energy. Now, very often we say that work requires energy, or energy is the ability to do work, but most often they're just considered plain synonymous. More precisely, an increase in the energy is always equal to or due to the work that is done on the system. So, what is this work that we do? Well, it's a force times a distance. We know what we do when we do work, such as mowing the lawn. We push a lawnmower and we push it a certain distance. We'll describe in a moment how we get the exact equations for that. But let me mention first that the work and the energy are scalar quantities, and they do not have any direction. Force, as you know, points in a given direction. It has a length, and you can't apply a force without pointing it in a given direction. We can't have a velocity without having a velocity in a given direction, or an acceleration. These are all vectors. But certain other quantities, like energy, temperature, and mass, are scalars. They do not point in one direction or another. In particular, energy is a scalar, and we'll see how that arises in a little while. Now, what are the different types of energy that we might consider? The first of these is kinetic energy. That's energy of motion. So when your car is going down the road or a football player is running down the field, he has energy by virtue of the fact that it's a mass that's moving with a particular velocity. Another type of energy is potential energy. It's the energy due to position or configuration. For example, if we have a rock that's up high on a hill or water that's in a dam, that represents potential energy because we could let the water flow out of the dam, the rock roll down the hill, and it could do work for us or accomplish something for us. So the first of those might be something like gravitational potential, whereas the water is behind the dam, or the rock is up high. But another one might be the elastic potential energy from a spring. We might compress that spring, and then we've stored energy in it, and we call that potential energy. We can also have chemical energy. The chemical energy is stored in potential chemical reactions of atoms and molecules. For example, if we have gasoline, we can burn that gasoline combining the hydrocarbons with oxygen, producing different chemical products that have a lower energy or can release energy as they go to lower energy states. Or we can take something like hydrogen and combine it with oxygen and make pure water. Hydrogen is a beautiful fuel because if you have hydrogen, of course there is not any, we have to make all the hydrogen we need. But once you have hydrogen, it's a good method of storage. In fact, for weight, it's about 5 to 8 times as much energy per mass as any other substance, gasoline or anything else. So it's a great way to store chemical energy is to store it in atoms and molecules, in particular something like hydrogen. Why? Because we can let that hydrogen burn or mix with oxygen, forming water, which has no pollution. Food is another example of a way we can store energy in calories. There we mean a capital C means a kilocalorie, or 1,000 of the small calories, and that's what we eat. We eat these thousands of calories. Like a banana has about 100 calories, that means kilocalories. We can have nuclear energy in addition to chemical, as you know. Coal is a standard chemical source of energy. For nuclear energy, we can have uranium, or we could have other types of substances that will fission when we put them in nuclear reactors, and that gives off heat that, just like the chemical reaction, the nuclear reaction can also give us energy, usually in the form of heat, which we then use to boil water and turn a turbine and go to a colder place, thereby going to a state of higher entropy, but with useful energy released. We can also talk about solar and radiant energy. This is like a our renewable resource, the sun, and we are constantly getting radiation from the sun, and we'll talk about how much that is later. Finally, another form of energy is heat. Heat is a random motion of molecules and constituents like atoms, and that random motion can, if we compare one thing that's at a higher temperature to something else with a lower temperature, we can actually extract part of that energy and make it useful. But generally, when energy goes into heat, it's something to be avoided because it's hard to get it back again, and we can never get it all back according to the laws of thermodynamics. Well, that kind of gives us an overview of these concepts of work and energy. Different examples of what they can be, the fact that energy is conserved as it's converted from one form to another with work. And more precisely, energy is always equal to the work that's done, so they're considered synonymous. And here are some types that we have just discussed.